This is StarTalk. I'm your host, your personal astrophysicist, Neil deGrasse Tyson, and I got with me today Matt Kirshen. Matt, welcome back, dude.
Thanks, Neil. How you doing?
Doing good, good. And you are host of your own podcast called Probably Science, and I finally got that right.
That is... Nailed it.
Nailed it this time. Yeah, I think I spent 10 episodes saying, is it could be science? Might have thought it could have been science. And so I'm still waiting
for... answer to any of those.
I'm still waiting for my next invitation because I enjoyed my one time that I appeared.
Anytime. I never want to abuse my connection to you, but the second you have a book to plug, a reason to be doing the rounds of interviews, we are jumping on that.
All right. Excellent. Excellent. So the topic of today is the James Webb Space Telescope, which is in all the news because it's been talked about for up to 2 decades now. I remember it was in some of our proposals in my astrophysics communities. We said, we could use an infrared telescope tuned to see the edge of the universe, and that same infrared would enable us to find planets. I remember thinking that through with my community, and now it's real. It's a real thing. So turns out we have 2 guests for this episode of StarTalk. First is Nathaniel Kahn, who is the director of a newly released documentary on, I think it'll be appearing on CNN, he'll tell us, where it's all about the making of the James Webb Space Telescope. And he follows the scientists and the engineers, and just you end up getting in the middle of it all. So we're going to talk to him in the first segment. And then after that, we're going to bring on one of the scientists who's looking for exoplanets to try to maybe replace Earth. Maybe they know something we don't. Can we hitch a ride with them? So let me first get on here. Nathaniel Kahn. Nathaniel, welcome to StarTalk.
Thank you. It's a great pleasure to be here.
Yeah, today's topic is we're going to talk about the James Webb Space Telescope. Ooh, this has been in the news for a decade and more. We proposed this even longer ago than that, and in the astrophysics community. It's a telescope that's very specifically tuned for very specific tasks. But before we get into that, let me introduce Nathaniel. Nathaniel, you produced a film. That's what you guys call it. a film, yes. a documentary.
Either one is fine. Movie's fine. A picture is fine. Film, movie, picture.
A talkie. Yes, he's produced a talkie.
A talkie. It's a talkie. Exactly. We're off to a good start here. Yes, indeed. It's a talkie. Yeah.
On the making of the James Webb Space Telescope, and it's called The Hunt for Planet B. And so you're the director of this film, and I'm flattered to report here that your team asked me to be interviewed for it, but I was swamped at the time that request came in. So you managed to make it without me. That's fine.
It was difficult. No. I'll tell you, it was difficult. No, we really wanted you. At least I'm here now. We're here now talking about it.
So one of the scientists you featured was Natalie Batalha, who, in fact, we will bring on to StarTalk in segments 2 and 3. But right now, we want to find out what was your thinking behind making this documentary?
Well, I mean, this is the biggest pure science mission that NASA has ever undertaken. And it's an international effort. It's the Canadian Space Agency, the European Space Agency, and NASA working together to build this incredible telescope, which you described, the Webb Space Telescope. And it's been, 2 decades in the making. It's 10,000 people have worked on it one time or another. If you do the math, it's thousands of human years have gone into building this thing. It is a telescope that the largest space telescope ever undertaken, and the biggest science mission NASA's ever done. So for a documentary filmmaker, it's thrilling to be able to watch this thing come together. I mean, it's like watching a cathedral being built or something like that.
Wow. So cosmic cathedral, if you want to alliterate that.
A cosmic cathedral, exactly.
A cathedral that's really hard to repair if something...
Well, it can't be. That's the thing. I mean, the stakes of this thing talk about also for
Matt, don't ruin his delivery. Matt, you just ruined everything.
No, you're not ruining my delivery. You're teeing me up. You're putting the ball right on the tee. The stakes for this thing could not be higher. I mean, we all know about Hubble, right? That when Hubble went up in what was it, Neil? Was it 1990?
90, 91, yeah, around there. Mm-hmm.
When it went up, there was a problem. And remember, I don't know if you remember, but Hubble didn't focus. The star images were blurry. And it was, it was considered, for a moment, people were calling it a techno-turkey, and, this is a big waste of money, but luckily astronauts could go up and fix it. It's only 250 miles over our heads. But the Webb Space Telescope is going to be 1 million miles from Earth. It's in this orbit called L2, out, 4 times further than the moon. It is not fixable. It has to work. First time, only time. You've got one swing at this thing, and it's got to go out of the park. So the stakes of this telescope are as high as they can be.
So I have to I got to correct something you said. You said that luckily astronauts could fix it. It was designed to be fixed.
Yes.
So to be deployed by the shuttle, and astronauts could return in the shuttle. So it wasn't so much luck as planning, but no one planned to have to fix it from Jump Street, right? So
right.
Yeah,
that's right. Right.
Yeah.
That's got to be the most. I've spoken to a few rocket scientists, NASA scientists, both through my association with this show and through other means, and I can't imagine anything more stressful than I wrote joking, and then I'll send them I'll file my script, and then I'll send them to the studio floor, and then the person will deliver them, and the audience may or may not laugh, and if they don't laugh, I'm like, I screwed up today, but there's another day. I don't have to watch that joke orbiting the Earth for the rest of my life, failing every time it passes me.
One shot to tell the joke, and it has to be not only the perfect joke, but the delivery has to be perfect.
And that joke costs society millions and millions of dollars.
Yeah, billions.
Billions.
Yeah, off by factors of thousands. But just a quick a quick backstory here. The James Webb Space Telescope is especially tuned to observe infrared light at an infrared wavelength that forming galaxies in the beginning of the universe, which at that time are emitting ultraviolet light. Over the lifetime of the universe, the ultraviolet light redshifts through the entire visible spectrum and lands in the infrared. So this telescope was tuned to see the birth of galaxies in the universe after they had redshifted for 14 billion years. It turns out infrared is really good for probing deep gas clouds and seeing what's going on there. And Nathaniel, tell us what's going on in the wombs of gas clouds in our galaxy.
Well, I mean, that's one of the great things this telescope can do. As you say, it can peer through these clouds of dust and gas that we could never see through before and actually see planets being formed. So this is something we really haven't seen very much before. A little bit we have, because there's been some infrared astronomy before, of course, very good stuff. But this telescope is exquisitely sensitive, larger, it's 100 times more powerful than Hubble, and able to see into these cocoons, these sort of pillars of creation, as they're called, where planets are actually coalescing, and we're seeing the beginnings of what we have now in this solar system 4.5 billion years after our solar system began. So we're seeing the very beginnings of, as you said, Neil, really the beginnings of the universe. We're looking back towards the very first stars, the very first galaxies, 13.5 billion years ago, when we'd never seen these stars before, never seen the first stars, never seen the first galaxies, and also never really seen into these dust clouds where new planets are being formed. And also, there's this kind of other ability the telescope has, which is really a lot of the focus of the film, The Hunt for Planet B, which is there are these exoplanets, which are planets around other stars other than our sun. And 25 years ago, we didn't really know that these existed. As Neil, as you said, we surmised that they did, but we didn't know that they were there. Now we know that virtually every star in the sky has at least one planet around it, which is astonishing. I mean, think about it. Go out at the night sky and look up, and you see that every star in the sky has at least one planet around it. And some of them have multiple planets. This telescope is able to look at some of those planets and actually look in the atmospheres of some of those planets and see if there might be elements that might indicate the possibility of life on those other worlds. So this is a game changer moment, a game changer instrument, and it's about to launch, just a couple of weeks from now.
So what I like about it is it's taking us to the nearest objects in the universe, which could be other planets that resemble Earth, and the farthest objects in the universe. People normally don't think of telescopes as having that kind of highly different dual capability, but JWST is that.
I was going to ask where it launches from, because I got to see my first rocket launch recently. There was most of them go from the East Coast, from Florida, but I got to see one of the ones that goes from just up the coast in California. It was the Armageddon mission, the mission that's going to be knocking an asteroid, and they launched from just up the road, near Santa Barbara. So I was like, why haven't I ever gone to one of these? So we drove up the coast.
Permission?
It was amazing.
Who gave you permission to call it the Armageddon mission? Who gave you permission to do the DART mission?
Hollywood did, Neil, where I live.
It's the anti-Armageddon mission is what it is,
to
right?
deflect the asteroid. Yeah. So where is this getting launched, Nathaniel?
So this is getting launched. I mean, get this. We don't actually currently have a rocket, right, in the United States big enough to launch this telescope. We need to go to the Ariane 5 rocket, which is the European Space Agency. Arianespace makes it. And it's going to launch from French Guiana. So it's going down to a place called Kourou, and there's a spaceport down there. And they have this special fairing that they've built, which is the part that actually encloses the telescope. This telescope is so big, they actually have to fold it up to fit into the rocket. It's a transformer telescope. It's an interstellar butterfly, if you will. It has a sun shield on it that's the size of a tennis court that could never fit in a rocket fully deployed. So all this stuff folds up into a cocoon, and it launches out 1 million miles from Earth on this rocket, leaving from Kourou, French Guiana. And it's an awesome sight.
In your film, how would you describe the balance of attention you gave to the science that we seek and the engineering marvels that it required?
Well, it's a fantastic question, and I wanted to balance them both, because too often the engineering doesn't get enough credit. All the glory goes to scientists. No engineering, no science. So the whole idea was to be able to follow this thing coming together. The technical challenges, I mean, there were at least a dozen new technologies that had to be invented just to make this telescope. So creating it, building it, and it's a one-off. I mean, it's never been done before. So all the challenges of solving these engineering problems, how do you make a telescope that folds up? How do you make this telescope that has a mirror it's 21 feet across? So this thing has to open up. Hubble's mirror is only 2.5 meters across. So this is 6.5 meters across, much bigger. So how do you solve all those challenges? And it's made of multiple mirrors that all have to focus to one point. Incredibly complex engineering problems. So following those problems, as well as the aspirations of the scientists. So the dreams of the scientists can't wait for this thing to get on orbit. They've been waiting for a couple of decades for it. So this kind of wonderful dialogue between the engineering making this thing, the scientists waiting for this thing, the dreams of humanity being launched out there 4 times further than the moon, that's the focus of the film. So it's this combination.
So it's one thing for a documentarian to come on the scene when everything's ready to go and interview people, but you actually shadowed scientists. For about how long did you do this?
Well, I was lucky enough to be able to document the process, and the telescope was delayed a number of times for obvious reasons, which is, as you're doing something new that's never been done before, you encounter problems, and the last thing you want is to launch something that isn't perfect. So I've been shadowing this for about 5 years now, which pales in comparison to some of these scientists and some of these engineers who've been working on it for 2 decades.
Well, the whole career, yeah.
It's a whole career. That's exactly right. And one of the things that I found so sort of moving about it was, we have so many challenges and so many problems in the world today. But to see the hopefulness of the scientists and the engineers working on this thing, the willingness, as you said, Neil, the willingness to put your whole career on the line and for something with an unknown outcome. We hope it's going to work. We've made taken every single contingency into account. We hope it's going to find amazing things. I'm sure it will. I have great confidence knowing the people that it will. But it takes a lot of faith, really, for the engineers and the scientists to put this much of their life into something. Faith, belief, love, passion for what they're doing.
Passion
and
is a good word.
To be able to document that and to see that passion and to experience it was, one of the great sort of joys of my filmmaking career.
So Matt, you don't put this much effort into a joke, I guess. Is that
Yeah, no, I've been working on the same joke since birth, and I've got a team of thousands.
It's your
and
material. Come on.
We
Your
got,
material.
yeah, we got some good international funding.
And you got to fold it up to take it into the club and then unfurl it.
and they don't really fit into the fairing, so I've got to work
Stretching
out
the metaphor there, but yes, right.
I do have one question, and
Yeah.
without sort of spoiling the film, but I know like whenever anyone makes a documentary, they always set off with a film in mind, but then it changes as you start filming and discovering. So what was the biggest sort of discovery or change in your mission as a filmmaker from what you set off to do and what you discovered in the process?
No, that's absolutely, you're absolutely right. And the really the sort of great thing about making a film that takes 5 years is that things happen that change your focus, and your focus begins to sort of, you begin to find, the film begins to find itself as you go along. And the way that I like to make films, I don't like to go in knowing exactly what I'm going to do, because then you're just kind of, you're telling a story that already exists. One of the great things about documentaries is you don't know where it's going to go. So in this case, it started out being fully about the building of the telescope. And as it went along, it really, this field of exoplanets became stronger and stronger. So I was able to then meet a lot of scientists, and many of them are women, which is a very strong aspect of the story, which is that, for years, much of science has been dominated by, it's dominated by the same old group that we always see, right? But exoplanets were sort of an area of science that was not as it was almost considered fringy. So a lot of people got into it who kind of couldn't advance in other areas. And so there were many people who flooded into that field, young people, people who weren't able to advance in other areas. And suddenly this field takes off. So I was able to document this kind of almost seismic shift in the world of astrophysics, in which we have these teams of people now doing great science. And many of them are led by some of these amazing women who were in the film. So being able to document that kind of seismic shift was terrific. That was one thing that happened. And the other thing was that at the same time we were making the film, the climate marches were happening. And young people around the world were talking about climate change and saying, look, there is no planet B. We only have this Earth. We have to take care of it. So suddenly, wow, there was the title right there that, well, the reality is out there, there are probably planet Bs. We're on the verge of finding these things out. However, we're a long way from being able to go to any planet Bs. We have to take care of planet A. We have to take care of this planet. So the kind of the interchange between the search for other worlds, allowing us to see our own world with fresh eyes, became a focus for the film that I can't say I started out thinking that way. It started out being documenting this amazing telescope, and it blossomed into this much, much larger story.
Okay, just admit it. You had a kumbaya moment in the movie. I did. Just admit it.
I did. No, it's like as a filmmaker, you're like, yes, we finally, we got something really great here. Something that's gonna mesh with some. You always look for something which takes you deeper. And as you say, it is the kumbaya moment. For a filmmaker where you realize, okay, wait a minute. This story that I'm telling suddenly has resonances that I didn't anticipate.
The cultural resonances.
The film is telling.
Yeah.
Yes, and actually, cosmic resonances, right? Global resonances. I mean, these are, these are things we have to contend with. And if a telescope like this gets us to think about ourselves as a global community, and that's part of this aspect of documenting the teams and the teams that built the telescope. You see the ability to solve nearly impossible problems.
Plus, they're real people.
Put our minds together.
They're real people doing it. Real people doing it, and it's your duty and obligation as a documentarian to capture that fact. So when I watch it, I can feel what they're feeling, and they become real to me, not just real in their own world.
There's There's even a love story in the film. So
Okay.
so it's
Is it between James Webb and Hubble?
no, I hadn't thought of that one before. No, it's not. No,
That's the next. That's the next one. Yeah. Yeah. All the space telescopes have a jamboree, and there's like love affairs that unfold out of it.
No, these telescopes want to stay far apart. They don't want to interfere with each other.
So where can we find it? Who's got it?
CNN has it, and CNN did a broadcast of it just last week, and it will be available. Continue to be available.
Okay, so will it land on CNN Plus because they have a new streaming platform? That's my guess.
Yes, it will.
Yeah. Okay,
absolutely,
right.
it will. It will indeed.
That's how we can find it. Okay, Nathaniel, we're going to send you away. That doesn't mean we don't love talking to you, but we got to make room.
Absolutely.
When StarTalk returns, we're going to feature one of the scientists who was featured in your film to talk about her research and what it means for her to search for Planet B when StarTalk returns. We're back. StarTalk, segment 2, all about the James Webb Space Telescope. And we thought, following on the heels of our documentarian, he featured several scientists, but one in particular we managed to bring onto StarTalk. And that happens to be Natalie Batalha. Did I pronounce that right, Natalie?
That was really good. Yes, Batalha.
Oh, Batalha. Okay. Thank you.
Batalha. No, you got it. I've heard all kinds of variations. You did great.
Excellent. So you're one of the lead scientists in thinking about planets and planet hunting with the James Webb Space Telescope. But your professional tracking, having read a bit of your bio, took you through the Kepler telescope. So just remind us what Kepler is and why do you care about other planets?
So Kepler was a space telescope too. It was a 1 meter telescope in space orbiting the sun. And its objective was to find potentially habitable terrestrial-sized planets. And it did that in spades. It found over 4,000 planets, many hundreds of which are the size of Earth, and some fraction of those are even potentially habitable or in the Goldilocks zone. So with the Kepler data, we were able to do demographic studies to understand the diversity of planets, to understand how common they are in the galaxy, to understand how many potential abodes of life there might be.
All right, so that's Kepler. So then why do we need JWST to look for planets if Kepler's sound like it?
Yeah, well, with most of the discovery techniques, all of the discovery techniques so far, what can we measure? We can measure bulk properties, the total mass, the radius, the orbital period, which via Kepler's laws tells us the distance between the planet and the star. So you know how much radiation it's receiving if you know how hot the central star is. Very basic properties. And one of the takeaways from Kepler is that the diversity of planets in the galaxy far exceeds the diversity of planets in our own solar system. There's all kinds of crazy worlds out there. And we want to understand that diversity because there will be implications for habitability and where these most likely abodes of life will be. So Webb gives us this new lens on exoplanet diversity. Instead of just measuring the bulk properties, we'll actually be dissecting the atmosphere and understanding what molecules are in the atmosphere. And that's going to give us insights into many of the details about that planet's history and nature.
So Matt, you heard she's on a one-name basis with the telescope. You heard her say that. Well, Webb will.
Yeah, Webby. Webster to his friends.
Yeah, well, I'm not there yet. I'm not familiar enough.
But you're calling it JWST, or what are you calling it?
I don't know. I will follow your lead. I'll follow your lead. So
J-Dog.
J-Dog. The Janeway Space Telescope. That's what we've been calling it.
So, Natalie, you're professor of astronomy at UC Santa Cruz. I visited that campus just once, and it wasn't real. It was like a movie set. I don't think it really exists.
My office is like living in a treehouse. Do you see the redwoods outside my window there?
Right.
Feels like I'm living in a treehouse.
And let's see if my co-host knows what the mascot is of UC Santa Cruz.
I do. I've got a friend who went there. It's the banana slug.
The banana slug.
Slugs.
Yeah, that's very cool and weird.
Well done. Well done.
So, Natalie, I don't know if you knew, but this is actually a Cosmic Queries segment. And we solicited questions from our Patreon members, and because they have exclusive access to our guests through this medium of questions and answers. And so Matt has collected them. And so Matt,
I have.
Yeah. So these are questions just,
you know what, this
generally about the telescope, about the search for planets. Oh, wait, before we go there, Matt, let me just ask, Natalie, this documentary is titled Planet B, where we spent the first segment speaking with its director. Are you planning something that we don't know about? Is there some escape ship that you'll let us in on? What's going on?
There's only enough room for me and my family. Sorry, Neil.
and your cat. Yes. Okay.
No, it's no secret. I told Nathaniel that I didn't care for that title. The reason I didn't care for it is because it kind of reverts back to this colonial language I'm trying to get away from. So I'm not finding other planets as a backup plan for planet Earth when it is destroyed. I care a lot about planet Earth. And if anything, it's just the opposite. The more you look for planets elsewhere, the more you love your home and the more you realize how precious it is. But looking for these planets that could host life teaches us something about the extremes of habitability and eventually about the sustainability of life here on planet Earth. So Nathaniel, I think, did a really great job of communicating that point through the film. So that made up for the title.
And in all fairness, the full title is The Hunt for Planet B, not Let's Secretly Go to Planet B After We Find It. So I just want to
hunt with our nets and our bows and arrows. Yeah.
Hitch a trailer to the back of the rocket. You can do that, right? That doesn't affect how things fly.
So Matt, what do you have for her?
You can water ski. I have so many questions, I'm going to try and get through as many as we can.
Let's do it.
Your Patreon patrons have gone all out on this topic. It is a big one. So let's start with Jeff Johnson asks, I think this is quite probably a size up even from this massive telescope, but Jeff wants to know, how big would a telescope have to be to see features like cities on planets in other solar systems?
Such a great question. All of the detection techniques we have so far, and now even the characterization techniques, they're unable to resolve the surfaces of planets. We don't even see them as a circle. It's just a point of light. In the best case scenario, you collect that light, maybe spread it out into a rainbow, and you look for all of these chemical fingerprints that are in the light. But that doesn't mean that we haven't thought about what such a future looks like, what technology would enable resolving the surfaces of planets. And what we've come up with so far, maybe the future will hold surprises, but so far we're thinking about a network of what's called interferometers in space, well separated out, kind of like the ALMA array of sub-millimeter telescopes in the desert. They work in concert. They combine their light, make use of the fact that you can spread them out over great distances, which gives you very sharp spatial resolution. So maybe that's something that we'll do in the future.
What's behind that is, of course, the bigger the telescope, the more resolution you have. So if you have multiple telescopes scattered across a landscape, they have an effective size that is the distance between them, right? It's not just one single lens. And so that's what Natalie's talking about there. And so, yeah, I look forward to that. But let me invert the question and ask, how far away can you still know that Earth has cities, given telescopes that we have? So where would you have to put JWST where it could see the cities of Earth? How about that?
So they say Webb can detect a bumblebee on the moon. Bumblebee smaller than a city, right? So how much smaller? What factor? Yeah. So like 1,000 times further away than the moon. So let's say at the edge of the solar system.
Yeah. Okay. Cool. Well, no, it should be able to detect, if a city is 1,000,000 times bigger than a bumblebee, it should be able to be put 1,000,000 times farther away and see a city.
Yeah, exactly.
Yeah.
Yeah, I'm still guessing that's not going to get us to the nearest star.
No, it won't.
But it will get us to the edge of the solar system. Turn around with a telescope like Webb and look at the Earth from the edge of the solar system. You'd probably be able to see city lights.
Okay. All right. Cool.
Actually, Dan Dymek asked a question similar to that, which is like, is there a reason we send singular telescopes rather than multiple smaller ones? And he says, I get that it increases complexity, but if the singular JWST fails, that's it, rather than an array of smaller telescopes which don't just stop working if one fails. So why aren't we sending lots of smaller telescopes up rather than this one massive one? What advantage do we get from this big one?
There are multiple advantages. I mean, what do telescopes do? First and foremost, they are light collecting buckets. So they help us to see further and fainter than we've ever seen before, just because they collect more photons. So you want big light buckets. This idea of combining light of multiple telescopes, which is the subject of interferometry, which we were talking about before, would be fantastic. Let's do that. The technical challenge, though, is that those telescopes have to be held in a very precise formation pattern. They have to be at such precise distances from one another that the precision is comparable to the wavelength of light itself, which is like a millionth of a meter, or even a trillionth of a meter. So that is technically challenging. We don't know how to do that with very high precision, at least in the optical right now, from space, right? So that would be even more expensive. So if we want to study exoplanets and we want to look back to the first 100 million years of the galaxy, when the very first galaxies formed, we need a very big light bucket, and that's what Webb is.
All right.
Very cool.
So it's all about buckets. It's a bucket thing. Yeah. So
I love that. Yeah, this incredibly complicated piece of equipment that
Just a
costs.
bucket.
and she's calling it a bucket. So wait, then we get to call it our bucket list. See what I did there? Is that good?
There we go. Yeah.
Well, along those lines, what is the first priority? What is priority one for the James Webb Telescope once it's in position? And what's the first thing either of you would like to see? And that question comes from Kevin the Sommelier. And I want to know back at Kevin, what is the best wine to pair with space? We know space has a smell. I've heard that on a previous episode of this show.
All right, let's see. High on my priority list. Well, I have a bias because I study exoplanets and I have so many burning questions that I want answered. So I really want to look at those first. But the other physics or astrophysics that we're doing is super cool. For instance, they say that we can detect traces of the very first supernovae that went off in the universe. That sounds amazing, to be able to see the very first galaxies, kind of the moment when the lights in the universe flicked on. That's tremendously exciting. To see the nearest galaxies in high resolutions to the point where you can make out individual stars and watch them being born in real time on a kind of a galactic scale is very exciting. We have these images from the ALMA array, which I mentioned earlier, which is this array of submillimeter telescopes in the Atacama Desert who are combining light to observe protoplanetary disks where baby planets are being formed today. We see the material. They end up looking like these complex disks of material that have structure like thin rings or spiral structure. And the current thinking is all of that structure is caused by the baby planets that are embedded in that dust and gas. With Webb, we will be able to find the planets themselves and make sure and verify that that theory that's what's creating this structure is due to planets. So that's all the other stuff. But what I'm really excited about is to observe exoplanets in order to resolve some longstanding mysteries. For example, one of the most common, actually the most common type of planet that Kepler identified, and it appears it's one of the most common types of planets in the galaxy, is a kind of planet we don't even have in our solar system. And we don't understand their nature. We don't understand if this is more real estate for life or if it's something completely exotic and different. Maybe it's an ocean world, a planet like Earth that's completely enveloped in an ocean. We don't know. So I'm very excited to observe those planets and figure that out. There's one planetary system called TRAPPIST-1 that has 7 terrestrial-sized planets orbiting it, 3 of which are in the Goldilocks zone, and Webb has the capability of being able to detect their atmospheres. That's another observation that's going to be done right away. And so I'm very excited to see what comes out of that.
All right, Matt, give me some more.
Okay, Daniel Skiri wants to know, with a myriad of systems, each of which must work perfectly, how confident or worried are astronomers that James Webb will deploy successfully?
Actually, before we commit Natalie to get her vote of confidence or not in the telescope, let's take a break and we will find out from Natalie how reliable is the engineering on the James Webb Space Telescope when StarTalk returns. We're back. StarTalk, the Cosmic Queries segment of our attention given to the James Webb Space Telescope. And we have one of the investigators of the science of the telescope who focuses on exoplanets. And that's Natalie Batalha. But help me again?
You got it right the second time. You're doing great.
Batalha, Natalie Batalha, yes.
Yeah.
Batalha.
Yep.
And it's been great just hearing you just wax poetic about what this telescope will do for us. And there's so many hopes pinned on it. People's entire career, engineers and scientists who it's been taking that long to develop the telescope, to conceive it, develop it, build it, and now to launch it, wait for it to get out there, and then have it unfurl. Matt, that question, bring it to me again.
Yeah, how confident are we that it's gonna do its thing, that it's going to get up there? Because we already established in the first segment with Nathaniel that there's no redos on this one. There's no sending astronauts up to fix this guy.
Is that going to stop us? No. We're going to dare mighty things and we're going to do it anyway. And I don't find that worry is a particularly useful emotion. It is what it is. And we do our best. And we make use of the, like $1.33 per taxpayer per year for 20 years cost. I know that's not trivial, and I'm not making light of it. But this idea that it will destroy our careers, I think, is not the case. If something, God forbid, goes wrong, then we'll pick up the pieces. We'll go back to the drawing board and do what scientists do so well, which is problem solve.
Natalie, we wanted you to weep or something, all right? Not just say everything. Yeah, there you go. There you go.
Oh my God. I'm so nervous. I can't see. No. Yeah, I mean, and I'm saying that from the perspective of, it's my career that's on the line as well, in addition to my daughter. So I feel it very viscerally. But there's a lot of archival data. There are other things that we will do, and we will go back to the drawing board, figure out what happened, and we'll do it better next time. The reality is that we want lots of telescopes out at L2 in the future. We want to be able to build them there, to service them there eventually. It's a great place to put telescopes. And in order to learn how to do that, we got to keep trying, sometimes fail, and hopefully most of the time succeed.
Natalie, that is so level-headed and rational a response to that question. And we were just hoping and expecting that you just be weeping. This is what's supposed to happen. People spend decades of their life and they're just, and you're just, well, that's how that cookie crumbles. And so I don't know which is better. I don't know.
I like it though, because it's all data.
It's just data.
Whatever happens, you've got data and you'll work out how to.
Damn, Natalie, being all sensible about it.
We have to be like a SpaceX and, just kind of have more of a mentality that failure is a part of it. I think that we progress faster when we allow for failure. This would be a tremendous setback, don't get me wrong, and it's a very expensive one. So, but NASA does this well, and I have a lot of confidence in the engineers.
And just to emphasize what you just said, or to highlight, I think people don't fully understand or embrace the meaning of failure on the frontier of discovery. And they think everything's got to work perfectly. Well, if everything worked perfectly, then you're not actually on the frontier, because that meant you made no mistakes at all.
It's an impossible standard, right? Yeah, and that only NASA's held to.
Yeah.
And rightly so, because it's taxpayer dollars. But there, if you can't have it both ways. You can't push the frontier and never make a mistake. Those two things are not synonymous.
Advice was given to me in my career by Martin Schwarzschild, who is a relative of the original Carl Schwarzschild of the Schwarzschild radius of black holes. he was a professor at Princeton when I was there, and he said, the day you stop making mistakes, that's the day you know you are no longer on the frontier. And that put it all in context. But anyhow, Matt, give me some more. And we'll try. This is our last segment. See how many we can put in. And Natalie, let's see if we can go to lightning mode.
Well, luckily, we've covered quite a few things just in the course of answering people's questions just over the course of Natalie talking. But Dylan wants to know, and Dylan's a high school senior, so I like the questions from younger people, wants to know what the telescope hopes to do that Hubble can't or isn't good at doing. And what discoveries do you hope to make that I might see, Dylan says, as I work my way through college? And this interests me as well, because we were talking in the first segment about how, Natalie, your entire field has gone in the course of the last decade even half of your career, not even half of your career, has gone from being this sort of tiny sliver of astrophysics to this massive world, as we've gone from maybe there being an exoplanet to being every star.
Yeah, that's right. I mean, in my career, I wasn't even an exoplanet scientist when I got my PhD. I was studying stellar astrophysics. Exoplanets didn't exist until the latter half of my grad career. So things are changing tremendously. What might we see that Hubble couldn't see? Well, first of all, we're looking at a completely different color space. We're going over to the infrared, where dust will glow and allow us to probe disk chemistry or star formation, the chemistry of star forming clouds. We have a big enough light bucket to see the atmospheres of planets smaller than the giant planets like these weird, mysterious super Earths or sub-Neptune type planets, even planets as small as a terrestrial sized planet. That's never been done before. We will have also a big enough light bucket to look all the way back to the very first galaxies forming in the universe. From that, we will be able to create a flip book of galaxy evolution from the start to the modern age of the universe. So all of these are new things that have never been done before, and what you should expect to hear about over the next 10 years.
Wait, Natalie, he's in high school. You can't use the phrase flip book, okay? You say, we're going to make a movie of the evolution of galaxies.
Isn't that the same thing, like a cartoon? Oh my gosh.
Cartoon flip book. Who knows what a flip book is anymore? Yeah, before talkies and before movies, you flip the images and they would move.
Oh
They'll just know it as like you look through the slits in the cylinder as you rotate you turn the handle.
Right.
And well, Quentin from Switzerland asks, and you've asked, do you expect to see different chemical compounds in the atmosphere of exoplanets, which you've already answered, and says, for you personally, what would be the most surprising or exciting thing for it to detect?
The thing I don't know about. Every time we put a new piece of technology into space, we lift the veil to some new reality that we couldn't have imagined before. So with Kepler, it was this mysterious new planet.
I get that. But you have now access to the chemistry of an exoplanet atmosphere. What molecule will excite you most in your molecule list?
I think NASA has a PR problem because we're going to be studying carbon dioxide, methane, just the kind of the typical greenhouse gases. And we're going to be doing it not in this beautiful color space that people are used to with Hubble, but we're going to be looking at rainbows. We're going to be looking at a bunch of squiggly lines. And when I see carbon dioxide, with Hubble, we see water features in giant planets. And we model that to imagine what the abundance of carbon dioxide might be, because we don't have access to that molecule in the tiny bit of color space that Hubble has access to. Now we're opening that up, and we'll see all of these carbon species like methane and carbon dioxide in addition to the water. And that's going to allow us to verify our models and to understand the climate of all of these exotic worlds. And in doing so, it's like you make them a real destination. Now they start to have a personality. They don't just have a mass or a radius. Now they've got a climate. They have a temperature structure. They have color. So it really makes these planets look like an actual destination.
Yeah, but you still didn't tell me your favorite molecule that you want to find.
we're going to be measuring.
No.
You're not gonna-
Stop. I'm talking about a planet that could have life. Give me a molecule that somebody's exhaling. What molecule are you looking for?
Webb was not designed to be a life finder.
Oh.
It's not. It will be able to detect the atmosphere of a terrestrial-sized planet, but it's not sensitive enough to detect oxygen unless we spend the entire 10 years observing only that planet.
Okay, got it.
And
That's
you're going
the
to do
answer.
that what? Sacrifice of all this other science that we need to do.
No, of course. Okay, I'm all with you.
Sense. So the Webb is not a life finder. However, going back to this mysterious class of planets, we're going to measure the ratio of carbon dioxide to methane, for example, these two molecules. That sounds super boring, except it's going to tell us what these planets are. Are they more like a Neptune that is like a scaled down version of Neptune, or are we starting to see the byproducts of geological activity bubbling up and being released into the atmosphere? So that's, to me, is very exciting, because then that would indicate more real estate for life in the future.
And like you said, it turns it from just an object to a world that you can imagine things happening on its surface. And that's a game changer, not only for our imaginations, but for storytellers who might set sci-fi tales in space.
You've just answered a lot of questions in that answer just then, because there's a lot of people who are asking about life. And so I'm going to ask Nicholas Godlove, who is a science student and is hoping to follow in your footsteps as an exoplanet scientist, grad student, asks about extrasolar objects, whether the JWT will help us find those. And said like Oumuamua. Oumuamua, there we go. And wants to say, and says, because we can't leave out the possibility of these things being alien, like a ship, a beacon, a waypoint, or debris, etc. But this is extrasolar. That means something that's not attached to a star, right?
The extrasolar, he means beyond the solar system, which my first.
Oh, okay.
Sometimes they're called not exoplanets, but extrasolar planets. But when he referenced Oumuamua, now I know exactly what he's talking about. Oumuamua is this asteroid-like object that we observed far away. I mean, we saw it projected on the sky. And what scientists could discern from the data is that was not an object that was gravitationally bound to the solar system. It was an interloper. It came from interstellar space and it passed by the solar system and went on its way. Now there's some questions that have been raised, whether or not that could be maybe not just an asteroid, maybe it was something intentional. So there you start to talk about technosignatures, or, even biosignatures, signs of life, signs of intelligence. So as far as I'm aware, there have not yet been any selected programs for the first year of Webb observations to search specifically for technosignatures. However, keep in mind that every time Webb takes data, it goes to a public archive, and that data becomes available to anyone all over the world. So anybody could go and use the archival data after the fact to go back and search for technosignatures on their own. So
Cool.
I imagine that will be done. I mean, that should be done with every piece of data that NASA takes, because all of it's in the public archive and it all can be searched for anomalies, anomaly detection or kind of weirdness.
Yeah, I want to see alien TV
I got-
shows. That's what I want to see. See what they.
Yeah, well, it's all public. It all belongs to people. I've got 2 questions left. Let's do these quickly. One's specific and one's general. Paul Love asks, does the new image of a moon-forming disk around the planet in the PDS 70 star system affect theories of how our moon formed? Or has that type of scenario already been ruled out for how our moon might have formed?
That's a really complex and very profound question. We don't fully understand all of the details about our own moon's formation, but all of the evidence points to the fact that it was a collision with a Mars-sized object that left as its remnant a moon-sized object. The object that he's referencing is a system that has been observed through direct imaging. We see this disk. If I had to posit a guess, I don't know the answer to your question, but if I had to posit a guess, I would say that the formation mechanism is very different for that system, because the planet in question is a giant planet. We're talking about very large planets. So the way that Jupiter, Saturn, Uranus, and Neptune formed their moons is very different than the way the Earth formed its moon. And you have the first clue that that's true when you look at the mass, like the mass ratio of the satellite to the planet. For the Earth moon system, we've got this gigantic moon for Earth size. So that just speaks to a completely different formation mechanism right at the start. And that's different from what you're looking at with this other system.
And just to be clear, there are many moons of Jupiter and Saturn that rival the size of our moon. It's just that Jupiter and Saturn are huge compared to Earth. So this is this ratio that Natalie's trying to hammer in there about why that matters. So thanks for making that point. Definitely. Matt, one last question you had.
I always like to finish on something that's a bit more sort of profound and a bit more general. But Zeki Majed says, how will the James Webb Telescope further shape this generation's vision of the world, as Hubble had done before it for the previous generation?
I like that.
Oh, gosh, I'm not a fortune teller, but...
Well, comment, how about this, Natalie? Comment on the PR problem that you cited. We got to love Hubble because of the beautiful color pictures it sent back to us. If most of what you're doing is spectra, is in the analysis of rainbows, then people will rely on the science you say comes from it rather than from their desktop picture that they put from the telescope itself.
Well, just quickly, Webb will take beautiful images as well. It has cameras on board that are taking images, so you will see some fantastic new vistas. But I think the transformational science is in the what we call spectroscopy. Neil will let me say that word. Other news outlets have told me not to say that word.
Well, you already said rainbow. You already said rainbow, so we'll kick it up a notch since we got the rainbow out of the way.
I snuck it in on you. So spectroscopy is the study of rainbows. And the rainbow of light carries so much information with it. That's how we learn about the universe. And so one thing Webb could do is to really seed this notion into the public consciousness about how we utilize rainbows to learn about the universe. That already would be a tremendous leap forward for our collective consciousness. But in addition to that, we're going to learn so much about all of these different objects. And really what I'd like to say is Webb might not be designed for life as a life detector, but it is one way station on the way there. And the Decadal Survey already put forward the plan for the next flagship mission beyond Webb, which will be that life finder. And it's going to make use of all of the physics that we learned about how planets form, evolve, and what makes a planet potentially habitable and where the most likely abodes of life are going to be, so that we are well positioned to use that telescope that comes later. And you will be alive, if you are in high school today, you will be alive when that first discovery of a living world hits the headlines.
Natalie, let me set you up for another hole in one here. If Hubble, part of why an entire generation embraced it is because it was taking data for their entire time they were in school. Hubble's sort of useful life generating images is 20, 30 years. People, elementary school, middle school, high school, college, Hubble was there for them. What is the usable lifespan of JWST? And when it runs out of sort of station keeping fuel or whatever it is that enough into the future so that at this L2 point, since you said earlier, that could be a place where other telescopes hang out, might it be a place that astronauts visit to maybe refuel it and keep it going?
Such good questions. Okay, first of all, humans, we fall in love by the fifth date? That's pretty quick, right? I made that up, that statistic. Yeah. I don't. Mm-hmm. Okay, but we fall in love pretty quickly, and Webb will give us 5 to 10 years. So it's baselined for 5 years, but it has enough consumables on board to last for 10. That is significantly different than Hubble, and it's out at L2 where it's not serviceable yet or now. The plan, I think, I've seen a little bit of, is to create a cislunar station. And from a cislunar station, it's like the International Space Station, but it's out closer to the orbit of the moon. And when you get out at those distances, you don't need a very big velocity kick. slingshot velocity, rocket velocity kick to get out to L2. It's easier. So if we can do that, we should be able to build telescopes at L2, service telescopes at L2, send astronauts out there and back. Keep in mind that the L2 is 4 times further away than the moon is. So it's a million miles away. It's quite a long distance. But even though that sounds really far and difficult, a cislunar station would help to make that a reality. And I do think that's part of the long-term plan, not within the next 10 years, though. So once the astronauts do get out there to L2 or their robots, it would probably be archaeological, not active.
Archaeological. Wow. I like that. So the future frontier science one day will be archaeological for a next generation. That's simultaneously beautiful and disturbing at the same time. Natalie, it's a delight to have you on this program. Maybe when first light happens with the telescope, we can get you back on and you can give us an update on how the science is unfolding after, of course, the engineering marvel, the unfurling of the telescope as it happens perfectly. And Matt, you'll come back for that, right? We got.
I will be there. I'm going to be out at L2.
Bring the band back together for this.
Yeah. We can compare it to my results, where I'm just going to be tying an iPhone 3 to a helium balloon, and we'll see who gets the better pictures.
That sounds perfect. All right, fingers crossed everything goes well. Thank you so much for having me.
Excellent. And Natalie, where do we find you on social media?
N Batalha on Twitter and Facebook.
And Matt, where do we find you?
Matt Kirshen on Twitter, Matt_Kirshen on Instagram, but I'm rarely there. Twitter's where I mostly am. So Matt Kirshen on Twitter and then Facebook.
And the name of your podcast, Mostly Science.
It is probably science.
All right. This has been StarTalk, the James Webb Space Telescope edition. I'm Neil deGrasse Tyson, your personal astrophysicist. Keep looking up.